Hello students, welcome to the chemistry class. We were discussing about aldehydes and ketones. Myself, Dr. Vijayalakshmi. In this video, we are going to discuss about reactivity of aldehydes and ketones. So as we already studied the structure of a carbonyl group, so carbon in the carbonyl group is trigonal. Here, when during the nucleophilic addition, the transition state has started and to form tetrahedral configuration. So here in the trigonal, initially the carbon hybridization is sp2, so it is trigonal, and when nucleophilic addition takes place, it becomes sp3 hybrid carbon, and finally when the product is formed, that is a tetrahedral product. So this is the substitution product. In this, carbon is attached with the two groups, one is R and another one is R dash. So R and R dash may be hydrogens or any alkyl groups or aryl groups. In aldehydes, R and R dash may be hydrogens, or one is R alkyl group and R dash may be hydrogen, or means in the aldehydes one is always hydrogen and another R group may be aldehyde or alkyl group or aryl group. But in ketones, both R and R dash groups may be alkyl groups or aryl groups. When R and R dash groups are bulkier groups in the carbonyl compound, the greater would be the steric hindrance. Steric hindrance means if two bulkier groups are very near to each other, then there is some repulsion force is there and it is called a steric hindrance. So if R and R dash groups are bulkier groups, then there is a greater steric hindrance, and also each alkyl group being electron releasing group, that is it having a plus I effect, electron releasing group, it decreases the positivity of the carbon. So for both these reasons, the nucleophilic attack on carbonyl carbon is retarded, or it is very slow in ketones. But in aldehydes, one R group is always hydrogen, only another R group is a alkyl or aryl group. So steric hindrance is very less, so reaction takes place normally. But in the ketones, due to it is expected that they show the steric hindrance, therefore the nucleophilic attack on the carbonyl carbon in the ketones is retarded or it is very slow. How the nucleophilic addition takes place? So again, there are two types. One is acid catalysis, another one is base catalysis. In the acid catalysis, proton released by acid combines with the carbonyl oxygen. Okay? Proton released by the acid combines with the oxygen, or it attacks the carbonyl oxygen and thus becomes the electron deficient. The carbon becomes the electron deficient. So positivity of the carbonyl carbon atom is increased and attack of nucleophile is enhanced. See, the first, the proton released from the acid is attacked by this carbonyl oxygen, so it becomes OH. For this attack, oxygen uses its lone pair of electrons, so it gets a positive charge. So when these pi electrons are shifted on oxygen, carbon gets a positive charge. So a nucleophile will attack to the carbon and it gives nucleophilic addition product. So this is how the nucleophilic addition takes place in acidic medium. Suppose in the basic medium, the nucleophile is generated from the conjugated acid. So this is a conjugated acid. So here conjugated acid, it reacts with the base and a nucleophile is generated in the presence of a base. Then addition takes place. So here nucleophile goes to the carbon because which is less electron or it having electron deficiency. So nucleophile goes and attacks to the carbon. So the electrons are shifted to oxygen. Carbon becomes plus. Nucleophile will attack on the carbon. Carbon, nucleophile, new bond is formed, O minus, and it takes hydrogen from the water or from the solvent and it becomes the addition product. So these are the two types, either acid catalysis or base catalysis. The nucleophilic substitution takes place in acid catalysis medium or base catalysis medium. So let us see nucleophilic addition reactions examples. The first one is addition of hydrogen cyanide. So as we know, in the hydrogen cyanide, H plus and Cn minus, it splits as H plus and Cn minus. H plus goes to electron rich species oxygen. Cn minus goes to electron deficient carbon. So it gives cyanohydrin, corresponding cyanohydrin. For example, acetaldehyde is taken, to the cyanohydrin is added. So it gives acetaldehyde cyanohydrin. Or in the ketones, when the two groups are smaller, then the nucleophilic addition is easy. Then it gives acetone cyanohydrin. So when hydrogen cyanide is added to carbonyl group, corresponding cyanohydrins are obtained. Let us see the mechanism of this reaction. This is a base catalyzed reaction. So in presence of base, hydrogen cyanide is in presence of base, nucleophile is generated. So Cn minus nucleophile is generated. This nucleophile goes and attack to the electron deficient carbon, that is carbonyl carbon. This reaction is slow initially and this nucleophile attacks the carbonyl carbon and an ion is formed, O minus. After this formation of an anion, the reaction becomes fast. It accepts a proton and gives cyanohydrin. So this is the mechanism of addition of hydrogen cyanide. So this is base catalyzed reaction. Another one, reaction with hydroxylamines. In the hydroxylamine, that is NH2OH, hydroxylamine, it becomes like condensation reaction here. Hydroxylamine reacts with carbonyl carbon. So it looks like condensation. Here H2O is removed and it becomes C double bond N. The oxime is formed here. When carbonyl group react with hydroxylamine, oximes are obtained. For example, acetone, when treated with hydroxylamine, it gives acetaldehyde oxime. Or when acetone is treated with hydroxylamine, acetone oxime is obtained. This reaction is a characteristic reaction of carbonyl groups. Let us see the mechanism, how this reaction takes place. In the hydroxylamine, the nitrogen contains lone pair of electron. So, carbonyl carbon is attracted by this lone pair of electrons and new carbon nitrogen bond is formed. For this formation of carbon nitrogen bond, here nitrogen loses a pair of electrons so that it gets a positive charge. One of NH bond electrons are given to nitrogen, so H plus is removed and it forms, after the proton transfer, it forms NHOH. And this proton from this nitrogen is transferred to oxygen, O minus, anion. So it becomes OH. But this is unstable intermediate. This is called adduct. It is a unstable intermediate is formed. As soon as this intermediate is formed, the reaction takes place fast. Adduct loses another proton. So this NH bond electrons are given to carbon nitrogen bond. The H plus is removed and when it becomes a C double bond C, this carbon oxygen bond is also broken. The electrons are given to oxygen so that OH minus, H plus and OH minus are removed totally as H2O and it becomes oxime. N double C double bond N OH. Oxime is obtained. Acetal formation, another one important reaction, acetal formation. In the acetal formation, the carbonyl group reacts with alcohols. So one is it reacts with alcohols and forms hemiacetals. These hemiacetals are unstable, so it undergo reaction with another one molecule of alcohol. Totally it reacts with two molecules of alcohols and forms acetals. This reaction takes place in presence of dry HCl. The carbonyl group reacts with alcohol, one molecule of alcohol, and it gives a nucleophilic addition product is called hemiacetal. But hemiacetals are unstable. As soon as hemiacetals form, they are going to react with another molecule of alcohol in presence of again dry HCl and gives acetals. Now these acetals are the stable compounds. So for example, acetaldehyde reacts with ethyl alcohol and it gives first hemiacetal that reacts with another molecule of ethyl alcohol and gives acetaldehyde diethyl acetyl, which is a stable compound called acetal. The mechanism takes place in two steps. In the stage 1, one molecule of alcohol is added. So hemiacetal formation takes place. In this, it is an acid catalyzed reaction. So carbonyl carbon is protonated. So H plus reacts with O minus. So that C plus carbocation is formed. This carbocation reacts with oxygen. So oxygen having a two lone pair of electrons, which is electron rich species, that reacts with electron deficient carbocation and forms carbon-oxygen new bond. For this formation of carbon and oxygen new bond, oxygen loses a pair of electrons, so it gets a positive charge. Now, OH bond electrons are given to oxygen and proton is removed. H plus is removed and it gives hemiacetal. So, this is first stage of the reaction, where one molecule of alcohol going to add to carbonyl group in presence of acid and forms hemiacetals. In the second step, so up to this the reaction is somewhat slow, but after the formation of hemiacetal is unstable, so reaction takes place fast. So again hemiacetals are protonated in presence of acid media. H plus reacts with electron rich oxygen. For that new OH bond, oxygen loses electron, so it gets a positive charge, and at this stage carbon oxygen bond is broken, the electrons are shifted to oxygen, so it is removed as H2O and this becomes C plus carbocation. Now the electrons from the lone pair electrons from the oxygen are given to carbon oxygen bond, so it becomes C double bond O. Here oxygen gets positive charge because it loses the electrons. Now O, in presence of another molecule of alcohol, electromeric effect, the pi electrons are transferred to oxygen so that the alcoholic group reacts with carbon. So new carbon oxygen bond is formed. Again OH bond electrons are given to oxygen, H plus a proton is removed, so it forms the OR dash, that is alkyl group is added, alkoxy group is added, and this is called acetal. So totally 2 molecules of alcohols are added, and that reaction is catalyzed by acid. So it is acid catalyzed nucleophilic addition reaction. In the first stage hemiacetals are formed, but hemiacetals are being unstable, undergo further addition with another molecule of alcohol in presence of acid and forms the acetals. So now these acetals are the stable compounds. The acetal formation is an example for the nucleophilic addition, that is monohydric alcohol. So how the reaction takes place with dihydric alcohols? So reaction with glycol, the example taken is a glycol, dihydric alcohol. So here it is ethylene glycol, 2 OH groups, so it is called dihydric alcohol. Again in the acid media, same mechanism is followed, and finally oxygen and 2 hydrogens are removed and it forms CO and CO, new bonds are formed. This is called cyclic acetal. In the acetal, here in between the 2 alkyl groups there is no any bond, 2 separate alkyl groups are there, that is alkoxy groups, but here it is a dihydric alcohol, so it gives cyclic acetal. So in presence of acid, aldehydes or ketones, so this is aldehyde, it gives a cyclic acetal. If a ketone is taken, then cyclic ketol is obtained. But ketols, when these R groups, alkyl groups are smaller groups, then only they gives ketols. But in the aldehydes, the reaction is fast because one is hydrogen. There is no any bulkier groups for the steric hindrance. So there is no any steric hindrance. The reaction takes place as usual and it gives acetals. Thank you students. In the next class, we will see some named reactions.